So we were basically at the topic of random variables. A random variable is a function defined from the sample space, which is big omega. And so this is the domain, and the codomain is the set of real numbers, which is R. And so we assign to each element, each elementary outcome, a real value. And by doing this, we are defining a function from big omega to basically to the set of real numbers. And actually, big omega itself may be the set of real numbers. It may be the case that that our sample space is the set of real numbers. Okay. So what makes a random variable is measurable. So it is not any arbitrary function. It is a function, but also it is F measurable in the sense that with respect to some sigma algebra, the pre-image of any Borel set. And so what is the pre-image of a Borel set? Basically, you take the Borel set on the real line and you ask yourself, what are the elements in the sample space that are mapped to this specific Borel set? So the pre-image of the Borel set will be a subset of big omega. So the question now becomes, is this subset part of your sigma algebra or not? If not, then you have, you don't have a random variable, because the random variable should be F measurable, which means that all pre-images of all Borel sets should be included in basically your sigma algebra. Any function that you define on a sample space is a random variable if you are able to include all subsets of big omega in your sigma algebra. That is, if you use your as your sigma algebra the power set. But this is feasible when omega is finite, when omega is countably infinite. But if it is uncountably infinite, you will have, and if you want to have consistent mathematical results, you will have to let go of the power set and to use just just a proper subset of the power set as your sigma algebra. Okay, and so in that case, yes, it may happen that the pre-image of some Borel set is not part of your sigma algebra, and then what you have is some function and not a random variable. Okay, so so we have a function from a big omega to R that is also F measurable. And the good news is that you do not really need to investigate the pre-image of every Borel set. What you need to do is basically to focus on infinite intervals going from minus infinity to x, small x, where small x is a real number. So you need to focus on the pre-images of those guys. If you show that the pre-images of those intervals for every small x in R are in the sigma algebra, then there is a proof that for every Borel set you can think of, its pre-image will also be part of the sigma algebra. Okay, and so this is basically the story of a random variable, which is neither random nor a variable. It is a function. It is not a variable. It's a function, and it is in fact a deterministic function. For every elementary outcome, for every element of big omega, you do a deterministic assignment to some real number on the number line. So it is basically a function. The randomness comes from basically being defined on the sample space. Okay, and the sample space is equipped with a sigma algebra and also with a probability measure. So that's basically where random comes from. But the function itself, going from big omega to the set of real numbers, is purely deterministic. Okay. And then we talked about basically the probability law of a random variable. And so the probability law of a random variable, now we are thinking of basically our R. Okay, so R will be our like big omega. Okay, and then we will have the Borel sigma algebra as our sigma algebra, and we want to have a probability measure, okay, which is denoted by this thing. So we have a deterministic mapping from big omega to R, Okay, however, because there is a probability measure that is defined on big omega, we can transfer it to the set of real numbers. And the way to do it is this. For any Borel set, what you do is that you go and hunt for its pre-image. Again, the pre-image will be the subset of big omega, all the elements of big omega such that x of small omega, so basically those small elements, are mapped to this Borel set. Now, by definition, for a random variable, this pre-image is a part of your sigma algebra. And since there is a probability measure that is defined on the measurable space omega and f, then actually for every pre-image, because every pre-image is in the sigma algebra, then actually the function, the probability measure will assign to every pre-image a real number between 0 and 1. So this will be the real number that we assign to any particular Borel set. Okay, so for a Borel set on the real line, go and obtain its pre-image, which will be some subset of big omega that is mapped to this specific Borel set. This subset of big omega, if we are talking about a random variable, this subset of big omega is guaranteed to be in the sigma algebra, and so it is assigned the number between 0 and 1 by the probability measure defined on the tuple big omega and the sigma algebra. So basically, this probability here is well defined. Okay, and it is not well defined if x is not f measurable. Because if x is not f measurable, then there is a pre-image that is not in the sigma algebra. So if we talk about the probability law of the original sample space big omega, well, this probability measure, it assigns probability only to the elements of the sigma algebra. Any subset of big omega that is not included in the sigma algebra is not assigned a probability. We avoid assigning a probability to it because sometimes actually we cannot do this in a consistent way if big omega is uncountably infinite. Okay, so basically this is a well-defined problem, and that's the reason that a random variable should be f measurable, so that we are able to do this transfer of probability law from big omega and the sigma algebra associated with it on the one hand to the set of real numbers and the Borel sigma algebra on the other hand. Okay, so this is basically the story of a random variable, and typically we can work with random variables and forget all about omega and sigma algebras in many situations. In very specific situations, it may be basically good to understand the random variable as it is a sort of formally defined, but sometimes you can just work with this measure space. And in many applications, actually, the probability measure, which is this guy, we do not really transfer this probability measure from big omega. In fact, in many cases, we do not even know what big omega is. We just assign a probability measure. So for instance, we can say that our probability measure is the Gaussian distribution. We believe that in this particular application, it is nice to assume that our observations, okay, or it is adequate to assume that our observations follow the Gaussian distribution. Okay, so sometimes actually we directly assume that we have reasons to know this guy directly. Okay, so so in practice, again, and that's the reason, like, you can study probability without knowing its foundations, because sometimes actually you can use the R and the Borel sets and P of X directly, and you may not have heard about Borel sets before. The reason is that Borel sets include the intervals, and typically when we compute probability in practice, we focus on intervals. Okay, so so you can just define things in terms of intervals. Okay, but formally we can define probabilities on any Borel set. Now, to characterize a random variable, you need the probability measure. You need this P of X, okay? And you know, for all types of, shortly we'll talk about the types of random variables. For all types of random variables, you know, we can capture the information about its probability measure using the cumulative distribution function, which is the CDF. The CDF is defined for every type of random variable that you can think of, okay, not other things. So we will talk later, you know, about the probability mass function, which is defined for discrete random variables, probability density functions for continuous random variables, and so on. So you know, so basically there are like things that are specific to certain types of random variables. CDF is universal. You know, you can define it for any random variable of your choice. Okay. So what is the CDF? So the CDF is denoted by big F, okay, because like later I will denote the PDF, the probability density function, with a small f. So this is big F with the subscript. In the subscript, you write the name of the function, the random variable, the F measurable function that you define on big omega, that's big X, and between brackets you put small x, and this is basically the probability measure on the Borel set. The Borel set, which is the infinite interval from minus infinity to some real number, small x. Okay, so if you define this thing for every real x, you know everything about your random variable. Okay, what is this probability again? Like in many applications, actually we assign this probability. We assign it. We say, okay, that we believe that, you know, this, you know, that it, you know, it belongs to this and that, you know, those widely used or famous distributions. Formally, you know, basically this probability by, it's a Borel set. This is a Borel set. So you do the same trick for any Borel set. If you want to know what is the probability of this specific Borel set, you visit big omega and you find the subset of big omega that is mapped to your Borel set. So you go to big omega and see, you know, the elements in big omega that are mapped to this Borel set here, which is this infinite interval from minus infinity stopping at small x included. Okay, and then, you know, you take this probability, and you know, it's difficult just to write down something like this every time, so I will just write it like this. So it's probability big X less than or equal to small x, as you basically you are used to like you know, handling probabilities. We will just write this simplified thing. What is the probability that big X is less than or equal to small x? Again, the story like is like a bit complicated, because like you need like a sample space and so on. But you know, this notation here will take over. I mean, because like life is too short like for writing everything using exactly how the probability measure of a random variable is defined. Now, for a function to qualify as a CDF, okay, it needs to satisfy 4 properties. And if any function satisfies those 4 properties, then it is a CDF of some random variable out there. Okay, so there are 4 properties for any CDF. And if you give me a function with those 4 properties satisfied, then this is a function of some random variable. Okay. Now I will mention those properties without proofs, and the proofs of them are typically done using continuity of probability. Okay, so what are those properties? So the CDF, as x goes to plus infinity, the CDF is 1. So the intuitive explanation is this. What is the meaning of the CDF as small x goes to infinity? So remember, what is the CDF? It's the probability that big X is smaller than or equal to small x. So what is this probability? What is this probability? Well, it is 1, right? Because for every elementary outcome you assign a real number. So you assign something that is actually less than infinity. Okay, so this is the intuition. Again, you can rigorously do it using continuity of probability and show that the limit as a small x goes to infinity of the CDF is equal to 1. Now, what about x going to minus infinity? To minus infinity, it means that you are talking about a probability as such, but with a minus sign. So what is the probability that x is less than or equal to minus infinity? Well, it's 0. It's 0 because we assign to every elementary outcome a real number, and real numbers are anything between minus infinity and infinity exclusive. We don't include minus infinity and infinity. Those are not real numbers. In this course, we will stick to those random variables as as initially defined, and there are in some situations we actually need to assign let's say plus infinity to the random variable. In that case, the CDF will not go to 1. The CDF will not go to 1 as x goes to infinity. It actually may go to number less than 1. So those are called extended random variables or defective random variables, and they are useful in things like in random processes, renewal processes, Markov chains, and so on. Most likely we will not encounter them at all in this course. So basically we are dealing with random variables as normally defined. Now a CDF, I will do this one here, which is that the CDF is basically right continuous. As a function, it is a right continuous function. What is the meaning of a right continuous function? Okay, so the CDF as a function may be discontinuous at one point or more. Okay, so this is x, and the CDF is not necessarily a continuous function. It may do something like this, and then there will be a jump, and then it do something like this. Okay, so there may be discontinuities. However, it is a right continuous function, which means that this is open. Okay, so if there is a jump, what is the value of the function at the jump? Is it basically the lower one or the higher one or something it is always the higher one. This is the meaning of right continuity. So right continuity means that it's not continuous. Okay, and we'll see this actually from discrete random variables. For discrete random variables, basically the CDF will have those jumps basically at the values at which the random variable is defined. So we have those jumps, but it's always the case that when we have a jump, the value of the CDF at the jump is the higher guy. Okay, and formally we say that any function actually is right continuous if f of x small x plus epsilon, and we take epsilon to 0 from the right. We take epsilon to 0. So typically the definition, it's a sided limit. So typically when you take the limit, you can approach from either directions. But here for the definition of right continuity, you approach from the right. So if you take epsilon going to 0 from the right, okay, so it goes down to 0 being positive, then this limit is actually the CDF itself, which again means that when you plot the CDF, this is what you see if there is a point of discontinuity. And finally, the CDF is a monotonically non-decreasing function. Okay, so it either increases or it remains constant. I mean, you may find the flat parts in the CDF where the CDF is basically flat. Okay, but it never goes down, it never decreases. Okay, so it is a monotonically non-decreasing function. Okay, so these are the properties of a CDF, and they are very important. And it's like a classical exercise in probability, in which like you have some function that is parameterized with parameters, unknown parameters, and saying, okay, find those parameters such that your function is a proper CDF. And you basically use these properties that the function should go to 1 as x goes to infinity, should go to 0 as x goes to minus infinity. It should be a right continuous function, okay, and finally it should be monotonically non-decreasing. Okay. So the types of random variables. For pure types, we have actually 3. Okay, so because actually you can have a mixture. So you can have a random variable like with a discrete component and an absolutely continuous component. Okay, so we can have mixtures, but let's now focus on pure random variables, and there are 3 of these guys. And the first one is basically the discrete random variable. So a random variable is discrete if there is a subset of the set of real numbers. Okay, this subset is either finite or countably infinite. It's either finite or countably infinite. The probability that the random variable, is in this set. So basically the probability of this set S under, the probability law of the random variable is 1. Okay, is 1. So basically this means that a random variable is discrete if it takes on finite or countably infinite values almost surely. With probability 1, it takes finite or countably infinite values. Okay, so this is basically the definition of a discrete random variable. Okay. Now, for discrete random variables, right? We define PMFs. Okay, so sometimes it is basically much more convenient rather than using the CDF, which is basically defined for all random variables under the sun. For the discrete random variable, it may be more convenient to use this specific function called the probability mass function, and the probability mass function is basically this one here. It's the probability, since the random variable takes on finite or countably infinite values with probability 1, we may ask ourselves, what is the probability that big X is equal to small x? Again, where small x belongs to some finite or countably infinite set. So this thing is basically the PMF. So I will denote the PMF as a P like this with a subscript which is big X, and then between brackets we have a small x, and this is exactly equal to this. It's the probability that big X, the random variable, takes this specific value small x, and small x is an element in either a finite set or a countably infinite set. It cannot be a member of a set that is uncountably infinite. Okay, so this is the definition of a discrete random variable. Okay, so let's give examples. Let's give examples to discrete random variables. This one here is the indicator random variable. Okay. So and let's do things like sort of formally by again imagining that there is some big omega and a sigma algebra, and we will basically define the random variable as a function from big omega to r. So here is how we will define our function. Here it is. So we will sweep through every element. We will sweep through every single element in big omega. Okay. And then what we will do is that we will assign, basically the number 1 or 0, depending on whether big omega is in some specified subset of omega called A that is included in the sigma algebra. Okay. So again, there is a set A, and it must be in the sigma algebra. What you do is that you basically say that if you examine every omega in big omega, if a small omega is in A, then you take this small omega and you map it to the number 1. If a small omega is not in A, then you take this small omega and you map it to the number 0. So from the set of real numbers, you just use 2, 0 or 1. So this is like sort of, what you may know as the Bernoulli random variable. You assign basically the numbers from a big omega to only 0 and 1, depending on this test. So you for every small omega, there is some subset of big omega A included in the sigma algebra. If a small omega is in this subset, then you assign it to 1. Otherwise, you assign it to 0. Now, the first question is like, if we want to do like things rigorously, this is a function defined on big omega. It's a function, right? So again, it's function defined from big omega to the set of real numbers. And specifically here, we take it from big omega and we use either 0 or 1. Okay, so this is how we do our assignment here. Now, who says that this function is indeed a random variable? Because we know that random variables are not arbitrary functions, right? They are basically functions that should be f measurable. So let's to make the argument complete, let's first argue that this is indeed a random variable. And so the test is to examine every Borel set in the form of an infinite set going from minus, an infinite set going from minus infinity to the small x. Okay, and you should show that for every small x you think of this function, the pre-image of this interval is part of your sigma algebra. Why is this basically indicator or this function? Okay, so let's be like pretend to be very objective, and let's just call this thing a function till we establish that it is really a random variable. Okay, so again, the test of being a random variable is that the pre-image of any Borel set should be part of your sigma algebra. Okay, so what if you take minus infinity and you stop at a small x that is negative? What happens? Is there any small omega that is mapped to a negative real number? No, because basically you just map to 0 or to 1, and so basically this is empty, and the empty set is part of any sigma algebra. Now you take basically again those infinite intervals, and now you take that x is living between 0 included but strictly less than 1. Then what are the elements of big omega that are mapped to 0, right? What are the elements of let's go here. Any element in big omega is mapped to 0 if omega is not in big A. So basically, what is the pre-image? It is a complement, right? Because every element in big omega that is not in A is mapped to the real number 0. So the pre-image of 0, so the pre-image of the interval from minus infinity to 0 or some positive number less than 1, this pre-image is just basically the elements in big omega that are not in A. That's a complement by definition. Is this part of our sigma algebra? Is this part of our sigma algebra? Yes or no? Yes, exactly, because yeah, it's from the properties of the sigma algebra. If I say that A is part of the sigma algebra, automatically sigma algebras by design, this is how they are constructed. If you include a subset of big omega, you should include its complement, so you will have a complement with you here. Okay, so correct. What if now, if you investigate the intervals and x now is greater than or equal to 1, so what are the elements in big omega that are mapped to any number that is 1 or more? Well, everything, because everything is just mapped to 0 and 1. So the pre-image will be big omega, and big omega by definition is part of any sigma algebra. And so basically this is a measurable set. And you can see here why basically A should be in the sigma algebra. If A is not, then we are not basically, then A complement is not, it may not be in our collection of subsets. So A is in the sigma algebra, A complement is guaranteed to be there, and hence every pre-image is in the sigma algebra. So yes, this guy is a random variable. This is true. Okay. Now, what about the CDF?
What about the CDF? Okay, again, the CDF is that we want to know the probabilities of those intervals. You know, again, we typically write it as probability big X less than or equal to small x, and those are the probabilities of those Poisson sets in this form, from minus infinity to small x. Again, let's do the three cases. Now, what is the probability that, you know, you go from minus infinity to x and x is negative? What is the rule? The rule is that you go to the pre-image. So if x is negative, then the pre-image is the empty set. And what is the probability of the empty set under any probability measure? It is 0. Okay, so the probability of basically the CDF for any negative x will exactly be equal to 0. Now, if x is equal to 0, and but it can be a positive number, but it should be less than 1, then what is the pre-image? We just did it. The pre-image is a complement. The pre-image is a complement. And so what is basically the probability of a complement? It is some probability. We know it is well defined. Why it is well defined? Because basically we defined a random variable on a measure space that is equipped with a sigma algebra, and that is equipped with a probability measure that assigns a number from 0 to 1 to any element in the sigma algebra. So the probability of a complement is well defined. This is something that you know it's a number 0.25 or whatever. Okay. And now the last thing, what if x is 1 or more? Again, the question is, what is the probability measure of the pre-image? The pre-image is big omega. Big omega is assigned the probability 1, so this probability is 1. So here is the CDF. Okay, it's drawn here, but let me draw it like in slow motion. So this is x. Now, if we are talking about negative numbers, the CDF is 0. Okay, so here at 0 itself, we will see the probability. But if we are talking about negative numbers, this will be 0. Okay, so the CDF will be the horizontal line. Okay, then what is the CDF at x equals 0 or x equal any positive number strictly less than 1? In that case, the probability will be this number. It's a number between 0 and 1. Again, it's depending on basically the probability measure on the sample space. So let's assume that this height here is the probability of a complement. And then our CDF will be a flat line. It is equal to probability of a complement. And this goes all the way to, to before 1. Okay, we should stop at 1. Okay. Now, are we done? Not yet, because then if x is greater than or equal to 1, then the CDF is exactly equal to 1. Okay, so assume that this height here is 1. Okay, and that's the CDF. Okay, so it is this probability, which means that it is the probability assigned to those Poisson sets, and we get those by knowing the pre-images if we want to do things formally. And so this is the CDF. So the CDF here, it has the 4 properties. Remember them? Limit as x goes to minus infinity is 0. Limit as a small x goes to infinity is 1. There, it is not necessarily a continuous function. So actually, we have 2 jumps here, but the function is right continuous. And so right continuous means that this is what you see if there is a jump. So if you see a function that looks like this at a jump, this is not a right continuous, this is a left continuous function, and it is not a CDF. A CDF may not be continuous, but it must be right continuous, and as also you can see, it is a monotonically non-decreasing function. It can remain flat, it can increase, but it never basically goes down. Okay, so this is basically the CDF of this random variable. What about the PMF? What about for discrete random variables? In many cases, actually, it is easier and more useful to work with the PMF, the probability mass function. So the probability mass function, we ask ourselves, what is the probability of big X equals small x, which is denoted as such? What is this probability? So here, in our case, we have just, we just have that big X can be equal to 0, or big X is equal to 1, because actually this is how we define our function. We just map to 0 or 1. So what is the probability that that the random variable goes to 0? Remember, this was basically the probability of A complement. It is mapped to 0 if small omega is not in A. So this is the probability of A complement. And it is mapped to 1 if it is in A. So this is the probability of A. And of course, the sum of these two guys is equal to 1. And this is, you can think of this again as the origin or the foundation of basically the so-called Bernoulli random variable. So the Bernoulli random variable is a random variable that takes the values 0 or 1, 0 with some probability, let's say P, and 1 with the probability 1 minus P. But typically, again, so we typically in this course, we'll use this notation, Bernoulli. So X Bernoulli P. And in this course, the notation will be that small b is the probability that the random variable is equal to 1. So small b is px1, which is the probability that x is equal to 1. And consequently, basically, the probability that x is equal to 0 will be 1 minus b. And you can use the Bernoulli random variable without even thinking about big omega, the sigma algebra, what is set A. You can forget about all these things, and you can just say, oh, I have a random variable that is, that is 0 with this particular probability, let's say 0.7, and 1 with probability 0.3. And you can live happily and do many things without like attaching things to basically a sigma algebra. Useful, but in some cases, like when we talk about convergence of random variables and more advanced stuff, sometimes you really need to go back to big omega and its sigma algebra. Okay, so this is an example of a random variable, and discrete. I must be specific now. Discrete random variable. Let's take another example. It's a bit more complicated example to see that you can like define things in a bit complicated ways. So let's now take as our big omega the closed interval from 0 to 1, the sigma algebra, the Borel sigma algebra on 0, 1, and the probability measure to be the uniform probability and the uniform probability measure. And let's do this type of mapping between the elements of big omega and the real line. Okay, so you take an element in 0 and omega. Okay, if the element is in the counter set, okay, so remember the counter set, it is this weird set in which like you have the interval from you start with 0 to 1, and then you start constructing it in steps. In the first step, you remove the middle third, okay, from the open interval from 1/3 to 2/3. Then in the second step, you remove basically from 1/9 to 2/9, and from 7/9 to 8/9, and you do this ad infinitum, and you construct something called the counter set. Remember, the counter set, it is an uncountable set. I didn't give the proof, but you can put it in 1-to-1 correspondence with the closed interval 0, 1, which has the cardinality C, and it's a set of Lebesgue measure 0. The length of, quote unquote, the length of this set is exactly equal to 0. So here what we do is that if you find the number living in the counter set, so what is the counter set? It is what is left after doing these infinite removals. Okay, and I argued earlier, that basically you may think that basically nothing will remain after removing the middle thirds, but no, actually all end points will remain, and you have actually the number of points remaining can be put into 1-to-1 correspondence with R. So it is a non-empty set, and in fact it is uncountably infinite, and each number you find in the counter set, let's say that you will assign to this number psi 0. Now, the numbers on the intervals removed at the nth step will be assigned numbers, and these numbers will be psi m. Okay, so basically in the first step of construction, we remove this interval here. Okay, so let's assign any number on this open interval to some psi 1, a real number psi 1. And now psi 2, basically any number from 1/9 to 2/9, 7/9 to 8/9 will be assigned the real number psi 2, and so on. So this is a way of defining a function on big omega. Okay, so from 0 to 1, you can think about the interval 0, 1 as basically a counter set, and every number in the counter set will be mapped to the real number psi sub 0, and the complement of the counter set, which are basically those intervals that you remove along the way, and what is removed during the nth step will be assigned the real number psi sub m. So let's take the first case in which all those numbers are just equal and equal to alpha. Okay. I mean, what does this mean? Is that every single number, whether it's in the counter set or in the complement of the counter set with respect to the closed interval 0, 1, will just be assigned to the real number alpha. Everything, so, you know, from big omega, which in our case here is 0 to 1, you just, from the real line, you just choose this alpha, and you map everything here to alpha. Okay, so this is our function x1, of alpha. Okay, now is it a random variable? You know, is it a random variable? Here I said that it is a random variable. It is called the constant or degenerate random variable. How are we sure that it is indeed a random variable? It is a random variable again by the test. What is basically the pre-image? So what is the pre-image of from minus infinity to x? Okay. So what is the pre-image x1 in? So when I write the function with -1 here, I don't mean the inverse function as you do in calculus. Here by this -1, I mean the pre-image. Okay, so this is the notation I'm using. It's not the inverse function. It is basically the pre-image. So what is the pre-image of this thing if x is less than alpha? So yeah, what are the elements in big omega that are mapped to a real line, that are mapped to basically the part of the real line that is strictly less than alpha? Nothing, right? Because you map everything to alpha. So basically, what is the pre-image? It is the empty set, and the empty set is part of any sigma algebra. What about if you take x to be greater than or equal to alpha? Well, everything, right? Because everything is mapped to alpha, so everything is mapped to the infinite interval from minus infinity to x, where x is alpha or more. So basically, the pre-image here will be omega, which in our case is the closed interval 0, 1. And phi and omega are part of any sigma algebra, so indeed this is a random variable. And because the random variable takes one value, which is alpha, you can say that you can think of it as like deterministic, okay? And if you call it a random variable, you call it the constant random variable, or it has another name which is degenerate random variable. So if I say degenerate random variable, it means that x is equal to some constant. It's sort of deterministic. X is equal to 0.7 or 15 or pi or whatever. Okay, and you may say, you know, well, this is something, you know, this is something that is not random. Well, I mean, you can think of it as random. You know, sometimes it is nice to include the deterministic stuff as random stuff. Okay, so that you can, you know, basically deal with everything as if it's, you know, random. Okay, what is the probability? Now, what is the PMF? What is the probability that x1? Well, x1 is just equal to alpha. This probability is 1. You know, it's 1 because basically every element in big omega is mapped to alpha, so the probability that x1 is alpha is equal to 1. And now what about the CDF? What about the CDF? Again, for the CDF, what is the probability of this pre-image? The probability of this pre-image is 0. Okay, so you have a small x here. You go to 0. So any x, sorry, this is alpha. Anything that is below alpha, it's, you know, the pre-image of minus infinity to small x, where small x is strictly less than alpha. Basically, the pre-image is phi, and phi is assigned the probability 0. But now, if you talk about basically small x that is alpha or more, the pre-image becomes big omega. And what is the probability assigned to big omega under any probability measure? 1. Okay, and so this will, from alpha to infinity, this will be 1. So this is the CDF that we have right here. Okay, again, it's a CDF with one jump at alpha, and remember, you know, so this is basically the value taken by this random variable, and you see that the jump is it's a jump from 0 to 1, like this. Okay, let's now do another assignment. And this other assignment is like, I will assume that psi 0 is basically, or let's start with those guys. I will assume that psi 1, psi 2, those real numbers are all equal to alpha. What does this mean? Any element on the closed interval 0, 1 that is not part of the counter set. So those are basically the numbers that are on the open intervals that are being removed during the construction of the counter set. Now, any number that is not that does not belong to the counter set will be mapped to the real number alpha. Okay, so all those will be mapped to alpha. What about the numbers that belong to the counter set? And we have an uncountably infinite basically number of those. All those numbers will be mapped to themselves. So if there is a number in the counter set, so for example, what is a number on a counter set? Like 0, 1/3, 2/3, 1, and so on. Each one of those guys will be mapped to itself. So 0 will be mapped to 0. So those are counter, so those, let's put it, they belong to the counter set. Okay, and there are so many of these, and each one of them will be mapped to itself. So now we are defining a bit more sophisticated function on basically on the sample space 0, 1. So in the previous case, we basically mapped everything to this chosen real number alpha. Now we will map every number that is not on the counter set to alpha, but every number that is on the counter set will be mapped to itself. So 0 goes to 0, 1/3 to 1/3, 2/3, and so on. Okay. Now, okay, so we did this type of mapping. So what are the values we map to? What are the values we map to? What are the values we use on the real line? We map our big omega, we map it to alpha, and we map it to all the numbers on the counter set. Okay, so there will be, so basically how many numbers are we using on the real line when we do the map? In the previous case, we are just using one number, which is alpha. In our case here, what are we doing if we do this type of mapping? We are using how many numbers on the real line? We are using an uncountably infinite number of points, right? Because we are using alpha, we are mapping every number not on the counter set to alpha, but every number on the counter set, which is uncountably infinite, is mapped to itself. So we are actually mapping to an uncountably infinite subset of the set of real numbers. However, the function we define is a random variable. It is a random variable. Not only this, it is a random variable that is discrete. It is a discrete random variable. Okay, so what is this? So let's first, basically like sort of do the test. It's like important like to move here slowly and like to make sure that we understand the formal definition of a random variable. So let's actually do this check. Let's verify that if I define a function that takes the counter numbers to each one to itself and basically the numbers not on the counter set to alpha, that this is indeed a random variable. Again, the trick is investigate the pre-image. You do not need to do so for any Poral set, despite the fact that this is the original definition, because some smart guys proved that you can only investigate the pre-image of the intervals in the form of, basically an infinite interval from -infinity to x, small x included. Okay, so what is the pre-image of this thing if small x is less than 0? Is there any element of 0, 1 that is mapped to a negative number? Here, for this specific exercise, I will choose alpha to be a number living in 0, 1, basically that is not in the counter set. Okay, so alpha is it's not negative. So nothing is mapped to a negative number. So if nothing is mapped to the negative number, the pre-image is phi, and phi is part of any sigma algebra by design. So but we define sigma algebras to be as such. Okay. Okay. Now, what if x is greater than or equal to 0, but is strictly less than alpha? But it is strictly less than alpha. What is the pre-image? In other words, what are the elements on big omega that are mapped to numbers now that go from 0 included, to alpha, but before alpha is not included? So what are those numbers? Now remember how we did the mapping. Though, for the numbers that are not in the counter set, those are mapped to alpha, and the alpha is not yet here. Alpha is not yet here. Exactly. So those are the counter numbers, the numbers in the counter set that exist from 0 to x. Okay, so this is basically the pre-image. So it's basically the counter set, the number in the, but not every counter number. It's because here again we stop at x. So this is intersection 0 and x. Okay. So this is the pre-image. Now, is this pre-image in the sigma algebra? Well, the counter set is a Borel set. On 0, 1. And the closed interval 0x is a Borel set. Actually, the Borel sigma algebra includes all intervals of your choice, open, close, and so on. And the intersection of two elements in the sigma algebra is also in the sigma algebra. So the counter set is in the sigma algebra. The closed interval 0 to x is in the sigma algebra. So the intersection is in the sigma algebra. We are good. So basically we are okay. Yeah, so basically I am solving for a specific case here, and basically you can do the others, because to solve this problem you need like to make an assumption. So is alpha negative, is it whatever? Okay, so I am doing for a specific case, and you can do the others, and if you are stuck you can basically talk with me. Okay, now if now you investigate the pre-image, and now x is greater than or equal to alpha, but is strictly less than 1. So now alpha is included. So what is the pre-image? Now remember that the elements not in the counter set are mapped to alpha. Okay, so basically what we have here is the counter set, basically intersection with 0 and x. Okay, and now also all basically the numbers not in the counter set, by definition we map them all to this alpha. Now you look here, is this part all I don't, psi basically those are, again, if those are in this particular example, what I am doing is that this is omega, which is 0, 1, and this is the set of this is the real line. The mapping is like this. So here, omega in the counter set, okay, so it is mapped to omega. So if omega is in the counter set, it is mapped to omega. If omega in the complement of the counter set, it is mapped to basically alpha. So in the complement of the counter set, all those guys are assigned the same alpha. The numbers, the elements of the counter set, each one is assigned to itself. So 0 goes to 0, 1/3 to 1/3, 2/3, whatever number is in the counter set, it's mapped to itself. So now if I ask you, what is the pre-image of -infinity to x, and now x is greater than or equal to alpha, okay, but it's less than 1. Now what are the elements that are mapped to alpha or less? What are the elements in the big omega that are mapped to alpha or less? Well, all the elements that are in the complement of the counter set are in our mapping, they are mapped to alpha. Okay, so now we have the complement of the counter set, and also we have the counter numbers that are basically from 0 to x, because those are mapped to themselves. Now everything here is in the sigma algebra. C is in the sigma algebra. C complement is in the sigma algebra. And for finite unions and intersections, everything is in the sigma algebra. Again, by the properties of a sigma algebra. So again, this is part of the Pauli sigma algebra from 0 to 1. Now, if x is greater than or equal to 1, again, the pre-image will be everything if we choose alpha to be living between 0 and 1. This will need to change again what if alpha is negative, what if alpha is, if alpha is 7 is equal to 7 or whatever. But the idea is that, what we have here, and regardless of your choice, you will get the pre-images all in the Pauli sigma algebra on 0, 1. And so we are indeed talking about a random variable. This is a random variable. But the question is this a discrete random variable? So, this is actually my point. Is this a discrete random variable? It is a random variable. You can check again that the pre-image of every basically Borel set on the real line is indeed part of the sigma algebra, which is the Borel sigma algebra on the closed interval 0, 1, which is big omega in this particular example. Question is this a discrete random variable? Again, if you look at basically the numbers we used when we did the mapping to the axis, to the real line, we used an uncountably infinite number of points because we mapped every number that is not in the Cantor set to alpha, but every number in the Cantor set is mapped to itself. And so how many of these do we have? We have small c of these, where small c is the cardinality of the continuum. It's basically the cardinality of the real numbers. However, this is a discrete random variable. Why it's a discrete random variable? Because now, what is the probability that big X is equal to alpha? What is this probability? What are the elements that are mapped? What are the elements that are mapped to alpha? What are the elements that are mapped to alpha? In our case here, for this choice of alpha, complement of the Cantor set, exactly. And I mean, for this particular example, so the elements not in C, exactly, the complement of the Cantor set. And again here I am choosing alpha to be a Cantor number other than 0 and 1. So for this particular case, this will be union alpha. Again, I am solving this, this pre-images for this particular case. You can choose alpha to be not not basically, it can be actually outside 0, 1. But again, for this particular case, those are the guys that are mapped to alpha. And what is the probability? What is the probability of those guys? The uniform measure, it's the probability of C complement plus the probability of alpha. What is the probability of a singleton? 0. What is the probability of the complement of the Cantor set? Okay, remember we did it in a previous lecture. This is 1, right? The probability measure assigned to the Cantor set is under the uniform measure. It is basically the Cantor set, it takes the probability 0, the complement takes 1. And if you remember how we did it, the complement of the Cantor set is simply a union of those intervals that we remove. And you can keep track of the length of those intervals, and you can show that basically the sum of those lengths is exactly equal to 1, which means that the probability of the complement of the Cantor set is exactly equal to 1. So what is the probability that X is equal to alpha? It is equal to 1. So X, exactly, so X belongs to a finite subset of R, which is the subset containing the element alpha with probability 1. We say, or X, we can write it, X is equal to alpha. Here this is random variable X2. X2 belongs to alpha almost surely. Does X2 have other values? Does X2 has other values that it takes? Yes. because basically we are mapping not just to alpha, we are mapping the numbers in the counter set to themselves. Exactly. So we have all those guys with us. Exactly. However, the random variable is a discrete random variable. Okay. So if you are using, if I tell you, define a discrete random variable, you do not define a discrete random variable by saying that it's a random variable that takes finite or countably infinite values. So here we have this random variable, it takes uncountably infinite values. Okay? Still, it is a discrete random variable. So the definition is this: X is a discrete random variable if it takes finite or countably infinite values almost surely. Almost surely. So the probability that X belongs to a finite or countably infinite set on the real line, this probability should be 1. This does not necessarily mean that basically that big X does not take other values. It may take other values, but those other values, their probability is 0. Okay, so again, this is, this example is specifically to make this point that basically a discrete random variable, the way of like defining it in a rigorous, or like correctly, is to say that it's a random variable that takes on values that are finite or countably infinite almost surely. But the mapping itself, the possible values of the random variable can be uncountably infinite. It's just the case that the probability of those guys, like here in the counter set, are simply equal to 0. Okay. So x2 here. So x2 here is, by the end of the day, I mean, from a practical point of view, what is the difference between this example and the example in which everything is mapped to alpha? From a practical point of view, nothing. Yeah, exactly. For all purposes, you will just deal with x2 as a constant random variable. It is constant almost surely. Okay? So for practical purposes, like x1 is alpha, x2 is alpha. x1 is equal to x2 almost surely. So this is a probabilistic statement. Despite the fact that x1 and x2 are defined in different ways, x1 really, you take every small omega and big omega and assign to it the number alpha, but x2 is complicated. You assign alpha to the non-counter numbers, you assign basically to the counter numbers themselves, each number is assigned, its value as the map on the real line, but x1 and x2 are equal almost surely or with probability 1. And from a practical perspective, that's it. I mean, x2 is alpha. Okay, x2 is alpha. Okay, but again, in advanced applications, you may find that it is important. So sometimes it may be useful, like, to make a distinction between x1 and x2. Sometimes you really need to go and revisit, basically the sample space and how actually the mapping is done from the sample space to the real line. In many other applications, no. I mean, you just, basically x1 is like x2. Despite the fact, that they are different functions. Definitely they are different random variables. But from a practical perspective, they are, and it is a correct mathematical statement to say that x2 is equal to x1 almost surely. If you just say x2 is equal to x1, that's wrong. I mean, formally, it's wrong. x1 equal to x2, this is wrong. x1 equal to x2 almost surely, this is correct. Because the probability that x2 is equal to alpha is equal to 1, because it happens that the probability of the complement of the counter set is equal to 1. Okay. So these are the discrete random variables. Here is like another discrete random variable, and it takes values that are so typically the discrete random variables, they take finite values. like the Bernoulli random variable, which is 0 to 1, or they take basically the natural, their value, they are basically they take the values of the natural numbers 1, 2, 3, 4, 5, and so on, or non-negative integers, and so on. So there are like several famous discrete random variables. We will encounter them later. So for example, the geometric random variable, it is a random variable. Basically x belongs to the natural numbers almost surely. And for the random variable to be geometric, you need its PMF. So this is the probability that x here x3 is equal to k. It looks something like this. It is 1/3, 2/3 to the power k minus 1. Generally, we have a number between 0 and 1. Okay, so the probability that x3 is equal to k is typically written as 1 minus p to the power k minus 1 multiplied by p, where p is some number between 0 and 1. Here it is 1/3. Okay, and I mean, for those random variables, we will deal with them later, and I think later in the course, like give you like a cheat sheet with the most famous or widely used random variables with their formulas and everything. Okay. Now, what about the other types of random variables? We have the absolutely continuous random variables. Okay, so the absolutely continuous random variables, to understand them, we need like to very briefly review this concept of a set of Lebesgue measure 0. Okay. Okay, so remember that basically probability spaces are special cases of measure spaces. Generally, for measure spaces, we have something called the measure function, and this measure function, the difference between it and the probability measure is that actually we allow the mapping to any number from 0 to plus infinity included, not just from 0 to 1. So this will be a general measure. And one of the most like famous examples of general measures are the Lebesgue measure, which is a generalization of the idea of length in 1 dimension, area in 2 dimensions, volume in 3 dimensions, and so forth. And basically, we have subsets of R to the n that are called basically null sets, or sets of measure 0, Lebesgue measure 0. Those are basically defined. Those are the subsets of R to the n, the n-dimensional Euclidean space, that can be contained in, that can be covered by boxes, by n-dimensional boxes, whose volumes can be, or whose measures can be made as small as we wish. If you can have a subset of R to the n, and you can cover it with a bunch of, intervals in 1 dimension, rectangles in 2 dimensions, cuboids in 3 dimensions, and so on, and if you can make the measure of these covers as small as we wish, then we have something called a set of Lebesgue measure 0. So in the first tutorial session, I proved this thing, that any countably infinite subset of R to the n is indeed a set of measure 0. Okay, so any set that basically you can put into one-to-one correspondence with the set of natural numbers is a set of measure 0. Okay. Let's just to, not to repeat ourselves and to avoid being bored. I mean, here is another example, that a line, actually a hyperplane in n dimensions is a set of measure 0. So let's briefly show that if you have a straight line in 2 dimensions, that it is indeed a set of measure 0, Lebesgue measure 0. Okay. So here is our straight line. Okay. And the first order of business is you need, so since we are talking in 2 dimensions, you need to cover this straight line with rectangles. Okay, and then you should be able to show that the overall area of those rectangles can be made as small as we wish. So here is the line, okay, and I will start covering it. Basically, the line can be divided into segments, each one of unit length, and then the interval from 0 to 1, I will cover it with a rectangle. So this width is 1, this width is 1, and then this height is epsilon over 4. where epsilon is some chosen positive number. I will do the same to cover this part from -1 to 0. Okay? Now, for the interval from 1 to 2 and from -1 to -2, I will cover it with a rectangle. The width is still 1 unit of length, but the height will be not epsilon over 4, but epsilon over 8. If epsilon is a positive number, epsilon over 8 is also a positive number. This rectangle is, smaller than this other rectangle, but it is a perfect rectangle, and it's covering from 1 to 2, and there is a similar guy covering from -2 to -1. Now, from 2 to 3 and from -2 to -3, we will cover with those orange rectangles. The width is 1 unit of length. The height, I will take epsilon and half it, this length here, and I will divide by 2 to have a height of epsilon over 16, and so on and so forth. So this is the cover. Okay, so we can take the straight line here, it is in red, and we can contain it. We can cover it with basically those boxes, which in 2 dimensions are rectangles. And basically, I will choose some positive number epsilon, and I will do this trick. I will cover, the part from 0 to 1 and from -1 to 0 with a rectangle with unit length as its width, and the height is epsilon over 4. From 1 to 2 and -2 to -1, the height will be epsilon over 8. From 2 to 3, -3 to -2, the height will be epsilon over 16. From 3 to 4, -4 to -3, the height will be epsilon over 32, and so forth. So we will get this cover here. Now, what is the overall Lebesgue measure of those rectangles? What is the overall Lebesgue measure? This Lebesgue measure, is basically, you can write the formula, but that you can find the area of each of those guys and sum the areas, and you will find that actually the cover here is by design, leading to a convergent geometric series, and you will find that the area of those rectangles covering the whole straight line in 2 dimensions, the area, or basically this is Lebesgue measure in 2 dimensions, is epsilon. And what is epsilon? It is an arbitrary positive number. We can choose it to be ridiculously small, 10 to the -1000, something like this. And so a straight line in 2 dimensions, a straight line, note a straight line in 1 dimension, a straight line has a Lebesgue measure of infinity because its length is infinity. But a straight line in 2 dimensions, its Lebesgue measure, which will be like its area, is exactly equal to 0. And this is, of course, this is the intuitive thing. You don't think of a straight line as having a positive area. It has an area 0, and this is like sort of the formal way of doing it. Okay, so again, even in n dimensions, a subset of the n-dimensional Euclidean space is said to be a set of measure 0. If you can cover it and with basically n-dimensional boxes, and then you can compute the Lebesgue measure of those boxes, and you find that this Lebesgue measure is upper bounded by something that can be made as small as we wish. So in that case, we will have the so-called Lebesgue or sets with Lebesgue measure 0. Okay. So this is a review of what we said, because this is integral to the definition of a continuous, or the formal name is absolutely continuous random variables. So what is the definition? An absolutely continuous random variable, and again for later in the course I may just use as you took in previous courses, I will just maybe use continuous, but the formal name is absolutely continuous because again it's something related to measure theory. So a random variable is absolutely continuous. Okay, something must happen. The probability of any Borel set, of Lebesgue measure 0 must be equal to 0. Okay, so a random variable is absolutely continuous if the probability of any Borel set of Lebesgue measure 0, the probability of this Poisson set of low big measure 0 must exactly be equal to 0. And so what are the Poisson sets with probability measure with low big measure 0, or singletons, or subsets of R with a finite number of elements, all countably infinite subsets of R, like for example the set of rational numbers, things like the Cantor set. All those guys, they have a low big measure 0, and so their probability, if we are using a random variable that is absolutely continuous, then the probability of all those Poisson sets should be equal to 0. So if we have an absolutely continuous random variable, exponential, uniform, Gaussian, gamma, chi-squared, non-central chi-squared, all those famous guys, then if you ask things like what is the probability that we generate a number using the Gaussian distribution and we obtain a rational number, well, the probability by definition is 0. The probability of any Poisson set with low big measure 0 is 0, and rational numbers have a low big measure 0. Okay, so this is the definition of absolutely continuous random variables. Now there is a powerful result in measure theory that tells you that if we have random variables defined in such a way, then there exists, okay, we are sure, we are guaranteed, we'll take this for granted, okay, we will not do basically the proof or anything. It's like, this is like heavy measure theory, beyond me. There exists a non-negative function. So for those guys, you can obtain a non-negative function which we will call the probability density function, the PDF. Okay, so it is a non-negative function. Okay, so you can always construct this non-negative function called the probability density function for those guys called absolutely continuous random variables, such that you can obtain the CDF, which is this guy, the probability that big X is less than or equal to small z, by integrating the PDF. So basically you can find this function. Okay, so this function is not for discrete random variables. This function you can define for absolutely continuous random variables. It is there, and we will take its existence for granted. And this function is not a probability. It's not a probability. Okay, it's called the probability density function, but it should be non-negative. And the integral of this function from -infinity to z will give you the value of the CDF of the random variable evaluated at z. Okay, so the PDF, the value of the PDF can be greater than 1, right? So so here, it should not be interpreted as a probability. So f of x small x is greater than or equal to 0. So this is something like probability. It should be non-negative. The PDF cannot be negative at all. However, can the PDF exceed 1? Can the PDF be greater than 1? Yes, it can be greater than 1. Not a problem. So long as its integral from -infinity to infinity gives you 1. Okay, so it can be greater than 1. In fact, the PDF does not need to be a bounded function. Okay, it does not need to be a bounded function. So let's take a function like this, f of x. Okay, and let's define it as basically 1 over square root x, maybe half, from 0 to 1, okay, and 0 otherwise. Okay, so let's think about this function. Can it be a PDF? It's non-negative. It's non-negative. It gets very, very, very high as x approaches 0 from the right. So it is unbounded. It's an unbounded function. So let's now check, whether, how is its integral. So its integral is from 0 to 1 over 2 square root x dx. And so what is 1 over 2 square root x? What is the basically the integration here? It is a square root x. from 0, 1. So it is 1 minus 0. So it is 1. That's a valid PDF. This function here is a valid PDF. For a very, very small x, this function becomes very, very large, much higher than 1 even, okay? So PDF is a different animal. It is not a probability. It is a probability density function. It is something, again, by measure theoretic arguments, you can show it exists for those, absolutely continuous random variables.